cs407 Numerical Analysis, Section 2.3 Tri-diagonal and banded systems. Note that tri-diagonal systems have nothing whatsoever to do with diagonality. If you're looking for a wand, I suggest you try visiting Ollivander's wand shop. Unfortunately, in this lecture, we're only going to cover tools that work in the Muggle world. So, we're going to do precisely what we said we're going to do in this section, that is work with tri-diagonal and banded systems. A lot of applications in linear systems have coefficient matrices with a banded structure. For example, ordinary differential equations and partial differential equations, when put into a matrix form, will often have this structure, so it's important to know how to solve them. In general, you end up with a lot of blank entries, so it makes sense to develop special systems that solve these efficiently and use far less space in the computer. So let's take a look at diagonal systems. So a tri-diagonal system is one where all the non-zero elements in the coefficient matrix must be on the main diagonal or on the two diagonals just above and below the main. So here is a picture of the tri-diagonal system. You can see the D sub I entries are the diagonals, and the C sub I entries are the super diagonals. So this is the super diagonal, the diagonal, and the sub-diagonal part of the system. Tri-diagonals are a banded type of system, and they're of practical importance in many applications. All the elements not displayed here, all the ones that would be up here and down here, are zeros. So let's look at this in a bit more mathematical detail on the next slide. As we mentioned on the last slide, all the elements that are not labeled are zero, and we can do this a bit more formally. So a tri-diagonal matrix is characterized by the condition A sub ij is 0 if I minus j is greater than 2, the absolute value of that. So if it's further away than 1 from the main diagonal, it's going to be a 0. In general, matrix is said to have a banded structure if there's some integer k less than n, such that you have that condition. And for the tri-diagonal, it's k is equal to 2, but the bandwidth of the system is said to be 2k minus 1. Obviously, the storage requirements for a banded matrix are less than those of a general matrix of the same size, since we don't need to store all those zeros. So an n by n diagonal matrix would only require n memory locations in a computer, and a tri-diagonal matrix would only require 3n minus 2. So we have quite a bit of space savings compared with the n squared. Now let's look at how we do Gaussian elimination for tri-diagonal systems. For banded matrices, the Gaussian elimination algorithm can be made very efficient if we know beforehand that pivoting is unnecessary. And of course, that makes it even more efficient. This section 2.3 of the book develops code for the tri-diagonal systems and gives a listing for the Penta-diagonal system, in which case you have a sub ij is 0 if the absolute value of I minus j is greater than or equal to 3, which means you can't be further than 2 away from the diagonal. And this situation occurs often enough that it can justify its own special procedures that we're developing, which are more efficient than the Gaussian elimination from section 2.2. So the procedure that we're going to make is called tri. And we're going to design that for solving a system of n-linear equations and unknowns. Tri will include both a forward elimination phase and a back substitution phase. We won't use any pivoting, so it'll be a bit more like our naive Gauss that we developed in section 2.1 than the Gauss procedure that we developed in section 2.2. So for step 1, what we're going to do is we're going to subtract A1 D1 times row 1 from row 2 to create a 0 in this A1 position here. This is only going to alter D2 and B2. C2 doesn't get changed because there's nothing that we're subtracting from it. So C2 minus 0 is still going to be C2. But This one, A1 will become a 0, D2 is obviously going to be altered, and B2 is obviously going to be altered by that multiplier. Now, what we're going to do is we're going to repeat this process for row 2 as the pivot after we're done with row 1 as the pivot. What I've done is I've included this tri-diagonal matrix so you can kind of see what's happening as we do this algorithm. So here's how the d sub i's and b sub i's are altered in each step, and you can probably see that on the last slide just by looking at the structure of the matrix. But d2 gets changed to d2 minus a1 divided by d1 times c1, and b2 is what b2 was before minus the multiplier times b1. And in the general situation we're going to have these two. Now, you can derive these, but they're going to be important when we actually write the pseudocode. At the end of the forward elimination phase, we're going to get a system in the following form. And here you can see that we've kept the main diagonal. Of course, some of these will get altered as a result of it, and we've kept the super diagonal. Except down here we have d sub n is equal to b sub n. So we can do that in the back substitution phase. We can get x sub n is equal to b sub n over d sub n and work our way back. Now this is the general form, and again the b sub i's and d sub i's are not what they were at the beginning of the process because we altered them during forward elimination. We did not modify the c sub i's, so those will be exactly the same. So now let's take a look at back substitution in a bit more detail. So back substitution again is going to start with x sub n and work our way all the way back to x sub 1 as we've been doing in solving using naive Gauss and Gauss. We're going to start at x sub n. And x sub n is going to be b sub n divided by d sub n. And then we can work our way back to x sub n minus 1, which is a bit more complicated, but because this is a tri-diagonal system, we only have to worry about the entries that correspond to the b and d's, and the b, c, and d's in that row. And we can work our way all the way back to x1, which is 1 over d1 times b1 minus c1 times x2. And in general, this is going to be the form of each x sub I if you're coding this up in the system. So here's the tri-diagonal procedure, and as you can see this is a lot simpler than the Gauss procedure we developed in section 2.2. So in this one we use a single dimensioned arrays for a sub I, d sub I, and c sub I for the diagonals of the coefficient matrix, and array b sub I for the right hand side. And we're going to store the solution array in x sub I. So those are all the parameters. N is the size, a is the coefficient array, d sub I and c sub I are also part of the coefficient array. We store each diagonal separately, and b sub I is the b vector, and x sub I is going to hold our solution. And the code progresses the way that we described forward elimination using the x multiplier, and to change the d sub i's and b sub i's, and we hold those a sub i's constant, as well as we change the a sub i's as well. The c sub i's get held constant throughout the forward elimination phase, and then we go back through the last for loop, does the back substitution phase. Notice that their original data in d sub I and b sub I get changed as a result of running this. Okay, an even more special case is the symmetric tri-diagonal systems. And here we can see that the sub and super diagonals are going to be the same. So c sub I for the subdiagonal, c sub I for the super diagonal. For these systems, you can use the same sub and super diagonals, obviously, and you can overwrite B with X. So at the end of the day, we only need 3 arrays, but we can still use procedure try. We just change the parameters that are passed to it. So here we would, instead of A sub I, we would pass C sub I, and D sub I is the same, C sub I, B sub I, and then for the solution vector, B sub I, which we can overwrite. As an application of these often arise in cubic spline functions, and we're going to see those in Chapter 6. So you may be asking, well, can this fail? And that's always an important question in numerical analysis. Since it doesn't involve pivoting, it's a very natural question to ask. You can get attempted division by 0 in some cases, even though the coefficient matrix is not singular. But if the tridiagonal system is diagonally dominant, then the procedure try does not encounter 0 divisors. So a general matrix A is going to be strictly diagonally dominant if the absolute value of the diagonal is greater than the sum of the A sub I j's and the other A sub i's there. So what does this actually mean? We have this mathematical definition. What does it mean in practice? Basically, the forward elimination procedures in try preserve the strictly diagonal dominance. In the last chapter, we saw that the number of long operations in Gaussian elimination was O of n cubed, but for these tridiagonals, it's only O of n. And another great thing with the tridiagonal systems is you don't need the scaled partial pivoting on strictly diagonally dominant tridiagonal systems. This means it's a real win for us. We've gone from O of n cubed down to O of n. Now let's take a look at another specialized type of system called penta-diagonal systems. These are 5-diagonal. So here we have our diagonal D, and we have 2 above, C and F, and 2 below, A and E. And the principles illustrated by try can be applied to matrices that have wider bands of non-zero elements, such as these pentadiagonal systems. Let's take a look at the pseudocode for solving the pentadiagonal system. So here's the pseudocode for penta. It's very similar to try. It's a little bit more expanded, but here we're placing the solution into an n by 1 array x sub I. Due to the last for loop, we shouldn't run this routine if n is less than 4. You can see here if n is less than 4, that's going to create problems from 1 to 1. It pretty much won't run if n is less than 4. To be able to solve these symmetric penta-diagonal systems with the same code and minimum storage, we've used our S and T up here to temporarily store some of the information rather than overwriting into the arrays. In the case of the symmetric ones, we can just change the call to penta and run the procedure with 4 linear arrays instead of the 7 that we've specified up here. And finally, let's take a look at block pentadiagonal systems. So a lot of mathematical problems involve matrices with block structures. In many cases, there are advantages in exploiting this block structure in the numerical solution, particularly true in solving partial differential equations numerically. So a penta-diagonal system can be described as a block tridiagonal system, where the A1s and C1s and D1s are blocks. So the block is just a very small matrix. And you can see how the small matrices are described down here. So you can imagine that D1 is going to be D1, C1, A1, D, or A2, D2. And we can put that in here. Same thing for A, and same thing for C. So it's just a more generalized system. Here we're going to assume that n is even. Say n is equal to some 2 times a number m. If it's not even, then we can basically pad it with an extra equation so that the number of rows is even. And the algorithm for block systems is similar to the one for tri-diagonal systems, except we're going to be working with small matrices, so that's going to add a little more complication to the code, because we have to solve those small matrices at each step. The results from the block Penta-diagonal code are the same as those from the procedure Penta, except we're going to have some additional round-off error. Also, this procedure can be used for symmetric Penta-diagonal systems, in which the subdiagonals are the same as the superdiagonals. The authors leave the pseudocode and the implementation of the code as an exercise for this, and later on in the text, about section 12.3, which I'm not sure if we'll get to, you can see how these systems get used for two-dimensional elliptical partial differential equations, such as the Laplace equation, which he does describe in this section to a small extent. So, next lecture we're going to get into some nonlinear equations and methods for finding their roots, including bisection, Newton's method, and the secant method, but we'll start with the bisection method.